After small technical difficulties, we are ready to start today's seminar. And our speaker is Alexander Perepechko, and he will speak about structure of unipotent automorphism groups. So, Sasha, please.
Thank you. I'm glad to be here. And today I have two aims. First, I wanted to survey some recent results, recent topics on automorphism group connected to unipotent automorphisms. And second, to present proofs of some results in the indicated preprint from a new version of proofs. So I think that I'll make a brief summary of surveys for survey. I'll skim some. I think that most of these results are known to you, so I'll just indicate some particular ones from the slides. If you want, I could send the slides in the chat, so we could open it independently. Would you like that?
If it is quick, Sasha, please send it. If it is not long time.
It will be okay. Open it. And okay, slides are sent. Good. So, first of all, the notion of multiple transitivity, it is a general abstract notion. An action of a group is called, on a set is called n-transitive. It is transitive on m tuples of points. And infinitely transitive, it is if it is n-transitive for any m. So any m points can be sent into any m points. For a finite group, if we consider the action as permutation subgroups, there are examples of symmetric group, alternative group, matrix groups, and all other groups are at most three transitive. For example, the automorphism group of a projective line or affine field. If we go to kinetic algebraic groups of an algebraically closed field of characteristic zero, well, they are generated by one parameter subgroups Gm, the multiplicative group of the field, and Ga, additive group of the field, and by theorem of Knop, the action of a kinetic algebraic group on an algebraic variety is at most two transitive, except for automorphism group of a projective line. So there are some examples of automorphism groups. If you take an algebraic torus, then the action from the group is one transitive. For an affine line is two transitive, and for affine space is infinitely transitive. And for unipotent subgroups, we don't have even two transitivity. Well, first let's define a unipotent group of automorphism. So an automorphism is called unipotent if it's contained in a GA subgroup of the automorphism group. So in a one parameter subgroup, which is isomorphic to the additive group of the field. And the subgroup is called unipotent, well, any abstract subgroup, if each element is unipotent, if it consists of unipotent elements. For example, if we take algebraic unipotent groups, well, they are isomorphic to subgroups of two-unit triangular matrices of upper triangular unipotent matrices. And by a result of H.Kraft and M.Zaidenberg, an algebraic unipotent subgroup cannot act two transitively anywhere on any orbit of Fn right. This is due to the fact that any action group acting transitively on a set of cardinality at least 3 has a trivial center. And the unipotent groups have some center. There's the notion two transitivity also appears in the context of flexible varieties. So we have a so-called special automorphism group, which is generated by JI subgroups by all JI subgroups of the automorphism group, and the transitivity of this S-out group on the smooth points of variety, and the affine variety is equivalent to infinite transitivity. This such variety will be called flexible. There are many examples of flexible varieties, but there is also an equivalence with two transitivity of the automorphism group. So the group S out is infinitely transitive if and only if the automorphism group is two transitive smooth points. This is true under the condition that the variety admits at least some one parameter action, GA or GM. But it seems that the condition of existence of such action is redundant and can be dropped if the following conjecture holds: that variety without any one parameter actions has a discrete automorphism group. This conjecture stands for at least 10 years, maybe more. And then, if it is true, then we have equivalence with the two transitivity of automorphism group. Okay, so another connected result is the T-time alternative. So let's take a subgroup of automorphism groups on a affine variety X generated by a finite number of JA subgroups. And if it acts two transitively, then it contains free subgroup F2. This conjecture was verified for affine surfaces and for affine toric varieties if the JI subgroups are homogeneous or generalized. And it seems that one could depose a more abstract, a more group theoretic version of this conjecture as follows: that group be generated by a finite number of unipotent elements. Then the group either contains a free group, or it is contained in an algebraic unipotent subgroup. And this conjecture is connected both to transitivity and to solvability of groups. And in recent years, there were also, yes, some questions? In recent years, there were also some results on automorphism subgroups under the assumption that they are solvable. That is, the study of Borel subgroups is active right now. So Borel subgroup of algebraic group of an ind on automorphism group is maximal solvable connected subgroup. So for algebraic subgroups, all algebraic groups of Borel are conjugate. And for the automorphism group, this is not always the case. For an FM plane, they are known to be conjugate, but for affine toric surfaces, there can be one or two isomorph classes. And for example, on an affine space of dimension S3, there are examples of Borel subgroups of derived length, 4 possible derived lengths from 1 to 4. And another results where solvability helps is if we consider subgroups generated by reducible algebraic subset. So let us subgroup G be generated by a reducible algebraic subset that contains the identity. So then G is connected. And if it is solvable, then it is a connected algebraic group. So it's algebraic. This new result by entirely get one sentence. And H.Kraft announced last year that a closed connected solvable subgroup is nested. So it means that it is a union of an ascending sequence of algebraic subgroups. Okay, so now we go to structure of automorphism groups. And the first general picture is as follows: that the automorphism group contains the neutral component. It consists of two morphisms that are connected to the identity by some reducible family. And the neutral component contains the subgroup generated by A out, generated by one parameter subgroups, and A out contains the S out group of special automorphisms. And the quotients, the first quotient of the whole automorphism group by the neutral component is at most countable. But the quotient of the neutral component by A out can be uncountably generated. So the gap can be huge. There is a conjecture that if all the A actions commute, then the neutral component is equal to the A out. And this conjecture holds for surfaces and for toric varieties, non-normal toric varieties as well. Okay. So let me finish with a survey and go to some definitions that are needed for our talk. First, if we have a derivation of the algebra function of x of our affine variety x, then it's called locally important if any function is annihilated by some power of d of derivation. And there is a bijection between locally important derivations and the unipotent automorphisms, which is given by maps by exponent to the one side and logarithm on the other side, which are computed as sums some infinite series like this. So here is the formula of an exponent. And since it's locally unipotent, then this series is actually finite for any. Okay. Cool. To describe all unipotent subgroups, we want to find some maximal ones. If we take, for example, linear general linear group, then any unipotent subgroup is conjugate to a subgroup of unipotent upper triangular matrices. And for the automorphism group, if we have an affine space, then there is a substitute for upper triangular matrices called the Jonquières subgroup of unipotent triangular automorphisms. We denote it by Jonc of nk index u. This consists of automorphisms that send each variable xi into itself plus some polynomial in previous variables. And it's as we see later, it is nested, so it is a union of the increasing sequence of algebraic subgroups. And it is exponent of a Lie algebra of derivations. We will be called Jonquières algebra, which is the direct sum of partial derivatives multiplied by polynomials in previous variables. This notion of Jonquière group and Jonquière algebra can be extended from the field K to any affine domain or any ring R. Well, we just substitute R for K in these definitions, in this formula. And after that, after this extension, we have a candidate for maximal unipotent subgroups in the automorphism group. Well, the inspiration for this work was a theorem by Zaidenberg and Kraft, that by Kraft Zaidenberg, that if nested unipotent subgroup externally on an affine space, then it's conjugate to a subgroup of Jonquière group. Well, we need this theorem is not true if we drop the transitivity condition. And we also need some equivalents for other varieties. So to formulate the result, we'll and to prove it, we'll need the notion of locally potent subset of derivations. So a subset of derivations called locally potent if any function any sequence of derivations, repetition allowed. When we apply them iteratively, we'll obtain 0 at some point. So in other words, if we have some function f and we apply some derivations, then we always get 0. We cannot avoid 0 at some point. Okay. So now I'd like to formulate the central lemma that allows to describe nested unipotent subgroups. And it is as follows. The central object here is Lie algebra L of derivations that is consists of locally unipotent derivations. Such algebras, as we will see, are equivalent to nested unipotent groups. So we have the Lie algebra of Landis, and we have its kernel A. Then there is an element of the kernel H and some algebraically independent elements, so next A over A, such that the localization of the kernel H is finally generated, and the localization of the real functions of X is just a polynomial ring over the localized kernel. And then our algebra L is contained in the Jonquière algebra over this localized kernel. This is the description, and it consists of 2 parts. Its proof consists of 2 parts. First part, it's theorem by splitting. If we extend our field to the field of fraction of the kernel, then our then the extended Lie algebra L is contained in the Jonquière subalgebra over the field F, over this field of fraction of the kernel F. This is the first part. This is the theorem by splitting. And the second part is to reduce from F of the field F to some localization of the kernel. To do that, we take a finite system of generators of the ring of functions of X. And we consider them as polynomials in our variables x1, xk. Then we take a common denominator of these polynomials, and we can choose a multiple of the common denominator so that the localization is finitely generated. So it is an affine domain. And then we have we imply that the localization of the ring of functions is a polynomial ring of a localized kernel, AH, and each derivation, well, it is a sum of partial derivatives multiplied by some polynomials over the field F. Well, since our derivations are regular, these coefficients are contained in the polynomial ring over the localized kernel. And this finishes the lemma. So now I would like to ask Andrei, are you here?
Sorry, yes, I'm here.
Yes. So, well, you specifically requested that I explain the proofs. So I ask you to tell me if is they comprehensible or not, or maybe I should skip some of them.
You do as you like. So I just.
Okay. So let me repeat the central lemma. The idea is that any linear subalgebra of derivations of LNDs is a subalgebra of Jonquières algebra over some localized kernel. And then such Lie algebra corresponds to but Lie algebras correspond to nested unipotent subgroups. That is, exponent of Lie algebra of LNDs is a nested unipotent subgroup, and vice versa. The logarithm of a nested unipotent subgroup is the algebra of LNDs. And here we need some small lemma on local unipotent subsets. Let me return to it. The lemma is as follows. Consider some finite locally unipotent subset of LNDs. Then they generate a finite dimensional Lie algebra. So this lemma, well, let me explain the proof, why it works. So first of all, let our set be D1 ds and take some function f. We call a function bounded if it is annihilated by any composition of n elements of our S, of our set, applied to f. We claim that any function is bounded. Indeed, if we have an unbounded function, then we can choose derivation so that the image D of f is still unbounded. because there is only a finite number of them. And then we can construct an infinite sequence of derivations, but at each point we still have unbounded function. So in other words, we can avoid zero indefinitely. And this contradicts the local nilpotency of our set. So indeed, for our Lie algebra, which is spanned by such which contains in spans of these compositions, applied to F is finite dimensional. And then the algebra itself is finite dimensional. And now, keeping this in mind, we also keep in mind that our algebra L, which is contained in the Jonquières algebra of localized ring, is also a local nilpotent subset. And now we can establish the correspondence between Lie algebras of LNDs and necessary unipotent groups as follows. If we have Lie algebra of LNDs, then we can choose an ascending chain of finite dimensional subspaces, union of the subsets equal to L, so our algebra. And by local nilpotency, because the Lie algebras generated by our subspaces are also finite dimensional. So our Lie algebra is a union of finite dimensional Lie algebras, and the exponent is a union of algebraic unipotent subgroups. We have necessary structure. And vice versa, if we have a necessary unipotent group, then the logarithms of algebraic subgroups UI that comprise our group U is a sequence of finite dimensional Lie subalgebras consisting of LNDs. And the union is again a Lie subalgebra consisting of LNDs. Okay, now we went from algebra to geometry and back. So what we get? The following description of necessary unipotent subgroups. For any necessary unipotent subgroup U, there exists a principal finite affine U-invariant subset X sub H, which is isomorphic to the direct product of some base Y and affine space. So it's affine cylinder with base Y and fiber affine space. So that our group U is contained in the Jonquières subgroup over the base. That's it. So this was the first part of the talk, the first result. Next, we'll go to the closedness. We'll prove that the necessary unipotent subgroups are closed, both automorphism group and the endomorphism semigroup. So, well, here are some. I'll skip a reminder that we have topology on automorphism groups first defined by Ramanujan locally and by Shafarevich globally in terms of varieties. And these two topologies coincide. Well, let me return. The automorphism group can be constructed as an ind group as follows. We have a union of subsets of automorphisms of bounded degree. So we bound the degree of homomorphism of its inverse. And then these subsets comprise is any sequence of closed algebraic subsets. This is in variety and an in group. But in fact, if we consider the semigroup of endomorphisms, this is also an in variety. Well, let's take any affine domain R over the field OK. This is a union of n-dimensional K subspaces. So naturally, this is an in variety. And assume that it has K generators from R1 to Rk. Then the endomorphism semigroup is naturally embedded into ring R to the power K, and it is closed there. It's defined by some equations. This is written, for example, in the survey by H.Kraft, and they have a result that the automorphism group is locally closed in the endomorphism semigroup. And this standard technique of intersecting closed subsets of some posing some equations can be formalized as follows. So let's consider some subset of f of elements of our ring R, and for each function in our subset, we fix the closed subset where we allow it to be sent to. And we consider the subset of all endomorphisms that send each function f into its prescribed closed subset S sub f. And of course, this subset is closed in the is closed subset of endomorphisms, since it is an intersection of pre-images of closed subsets under the action map. And then we can easily prove that the Jonquières group, well, the unipotent Jonquières group over the ring is closed in the endomorphism semigroup. Indeed, we send each variable xi into a closed subset xi plus polynomial ring in previous variables. So this is the shift of some subspace. So this is closed. Moreover, a more delicate and strong assertion is that the exponent map is an isomorphism of the varieties of Jonquières algebra and Jonquières group. Indeed, we can choose some fixed filtration of the polynomial ring over R by finite dimensional subspaces, finite dimensional in the base field F, in the base field K. And then these finite dimensional subspaces generate finite dimensional Lie subalgebras. Well, I'm sorry. Then the Jonquières subalgebra can be exhausted by finite dimensional Lie subalgebras. Moreover, exponents, when we take exponents, then the next structure coming from exponent of Jonquières algebra, and the in structure induced from the endomorphism semigroup, they coincide. They are equivalent. And this moment is sometimes neglected, but a very important one. So, okay. the exponent map is an automorphism of varieties of Jonquières subalgebra and Jonquières group. And the Jonquières group is closed in the endomorphism. That's over some fundament R. Okay. And there are also some, we have some lemma that the intersection of the endomorphism of variety X and endomorphism of its principal subset X sub H is closed in both endomorphic group of S and X sub H. And we conclude that an necessity unipotent subgroup is closed in both the endomorphism semigroup and automorphism group. And we proceed as follows. We'll need some closed embeddings. Let L be the Lie subalgebra corresponding to our group U. And let H be an element of kernel, and then L is Lie subalgebra of the Jonquières algebra, as before, over the localized kernel. I'm sorry, it should be a localized kernel. Okay. And then we have closed embeddings as follows. The Lie algebra L of our necessity unipotent subgroup is closed in the Jonquières subalgebra. Then the necessity unipotent subgroup is closed in the Jonquières group because we have isomorphism of invariants. And Jonquières group is closed in the endomorphism of the principal subset X sub H. So U is actually closed in the intersection of endomorphism semigroups of variety and principal subset, and which is closed in the endomorphism of X. And since automorphism group is locally closed in endomorphisms, then U is also closed in the automorphism group. We have our result that necessity unipotent subgroup is closed. Now we can go to next result on connected nested subgroups. Well, from here we can derive that connected nested subgroup is also closed in the automorphism group. And we need two facts. First, we have a decomposition of a connected nested subgroup into a semi-direct product of a Levy subgroup L, which is a reductive algebraic subgroup, and nested unipotent subgroup U, which is the unipotent radical of our group. And then there is some maybe technical proof that it is closed, which I won't go through. It is present here in the slides. You can check them independently. But I would like to emphasize that we use here equivalence of two structures on our unipotent radical U. We have a structure of a nested group, so an filtration by algebraic subgroups. And we have a structure of an in subgroup, we have filtration by degree of automorphisms. And these two filtrations coincide. This is crucial for the proof. Okay. So I stop with this result and go further. well, of course, not every nested group is closed, because if you take a torsion group, it is nested but not closed. And next, would like to describe maximal nested unipotent subgroups. This, well, to describe maximal subgroups, I'd like to introduce the notion of width. If we have some abstract subgroup of automorphisms, then we take a general orbit of the group, and the dimension of its closure is called width. And the nested unipotent subgroup is called Jonquières-like if it is maximal among nested unipotent subgroups of the same width as our group J. So it's not maximal unipotent subgroups, but maximal unipotent subgroups of given width. Why we introduce such term? If we consider what we obtained before, well, any subgroup was contained in the localized in the Jonquières group over the localized kernel, and this thing will exactly be our Jonquières subgroup. And there is also an alternative description of such a subgroup in terms of LNDs, of tuple of LNDs. So when we constructed our Jonquières subgroup of localized ring, we had some variables xi, and we have some partial derivatives. These partial derivatives don't have to be regular on x, but after multiplying by some power of h, they become regular. And then, in terms of the derivations d1, dk, we can describe our subgroup in terms solely in terms of this couple of derivations as follows. We take each derivation, we multiply it by a kernel of all derivations from di to the end, to dk, and localized by the kernel of the whole group A1. And from this big set, we take only regular derivations. This is the Lie group, the Lie algebra of our group, which we call D beautiful of our tuple derivation. This exponent we denoted by J beautiful. So what I described here is equivalence of three descriptions of such groups. This equivalence will be formulated as follows. First, such a tuple of LNDs, d1, dk. Well, we called it before generically free tuple, but maybe it's better to call it generic frame. Well, a tuple of LNDs is called a generic frame if they pairwise commute. And their vector fields are linearly independent of the general point. And now we have an equivalence of three descriptions in terms of a subset of LNDs as follows. Assume that we have some number k and a subset L of LNDs. Then the following conditions are equivalent. L is a Lie algebra of some dg-like subgroup of width k. L equals d beautiful of d1 dk for a generic frame, some generic frame d1 dk. And third, the L equals Jonquières subalgebra over a localized kernel of L. intersected with regular derivations. And in fact, we may assume that our derivations act on our coordinates xi like partial derivatives multiplied by h. So di applied to xj equals h if a equal to j, and 0 if not. So in other words, our coordinates x1, xk comprise a local size system for derivations d1, dk. Oh, this is object that we would like to study. Well, here's some proof, but I think I'll skip it altogether because it's more or less technical. But I'd like to express this proposition, this equivalence, in terms of groups, not of algebras. First, G-like subgroup, which is maximal of given width, equals J beautiful of d1 dk for some generic frame d1 dk, vice versa. Any such subset J beautiful is a G-like subgroup. And the second result is more interesting. It is on co-flags of fibrations. So we have a G-like subgroup of this K. Then it can be described as a stabilizer of a certain co-flag. More precisely, there exists a co-flag of A1 fibrations of affine schemes. So there are some maps P in I. So that J, our G-like subgroup, consists of all unipotent elements that stabilize the co-flag, and they are trivial on the last element of co-flag, on X1. And this co-flag is constructed just by taking spectra of intersections of kernels. So we take first X itself, then the kernel of decay of last derivation, then intersection kernels of two last derivations, and then of three, and so on, until we obtain, and A1 will be intersection of kernels of all derivations. And then the spectra are exactly these affine schemes and natural maps corresponding to the inclusions of algebras are A1 fibrations, because the general fiber is J orbit of corresponding to LND from our generic frame. And conversely, if some unipotent element stabilizes the flag is trivial on X1, then we can show by local unipotency that it sends variable xi into polynomials or localized kernel in previous variables. And then it is exactly inside the algebra of G-like group J. So this we can deduce the corollary that G-like subgroup corresponding to a generic frame D1 dk contains subgroup corresponding to a tail of this tuple of this frame di dk for any I. Moreover, if one go in it's more technical proof, one can show that the only digit-like subgroups contained in R, and one corresponding to D1 decay, are exactly this, of this form. So a digit-like subgroup of this K contains only K plus one digit-like subgroups, of which 0, 1, etc. to K to itself. And now I'd like to present examples of maximal unipotent subgroups. So let J be a maximal nested unipotent subgroup of width K. And what are the possibilities in low dimension? Well, if width K is equal to the dimension of variety, then our variety is an affine space, and our group J is just the Jonquières subgroup by theorem of H.Kraft and M.Zaidenberg. Okay. Let's go to dimension 2 case.
Okay.
If we have an affine plane and the width is 1, then our digit-like subgroup is generated by a generic frame that consists of only one LND. And by Resh's theorem, in some coordinates, it is just a partial derivative multiplied by some invariant. And then the digit-like subgroup is just exponent of all replicas of the partial derivative. And this is contained, it is not maximal, it's contained in the Jonquières group. Okay. If dimension is 2, but our surface is not affine plane, then the maximum possible width is 1. And any digit-like subgroup is of width 1 and commutative. So all necessary unipotent subgroups are commutative. Finally, if we have an affine space of dimension 3, then all three possibilities occur. So we have maximal unipotent subgroups of width 1, 2, and 3. For width 3, we just take the Jonquières group. For width 1, we take an LND of rank 3, which kernel does not contain a variable. It means that for any for any choice of coordinates on affine space, kernel doesn't contain a variable. And then this LND cannot commute with any other LND. And it gives a maximal commutative, a maximal digitalized subgroup which is commutative. Finally, the case of width 2 is obtained from the Nagata automorphisms from the example by Bus. We take a derivation d x multiplied by partial derivative in y and plus 2y multiplied by partial derivative in z. And this element of the kernel is d minus y squared. The exponent of d multiplied by f can be conjugated into the Jonquières subgroup, but our derivation d commutes with the partial derivative in z. So this Jonquières, this digitalized subgroup generated by two LNDs contains the automorphism, the Nakata automorphism, but and is maximal because it is not conjugate into Jonquières group. These are our examples. So if we go beyond nested, well, we have the following result. So we need actually two conditions. We have some unipotent group. We assume that our field is uncountable and use generated by JA subgroups. And we need this because the subset of unipotent automorphisms is not necessarily closed. We don't know if it is closed or not. The automorphism group. So the result is as follows. Assume that the field is uncountable. Then the unipotent subgroup generated by JA subgroups is nested. And any arbitrary unipotent subgroup is closed if and only if it is nested. So we have these two statements of our theorem, and I'll stop here, I guess, because it's time. Thank you.
Tosha, thank you very much. But we are intrigued by the number of slides. So you stop on slide number 40 something, and you have 57. Maybe you can just show us what remains here.
Okay, I'll just show that. So to prove this theorem, we have two lemmas. First, we consider the bracket closure of the logarithm of our u. It consists of LNDs. And from this, using main methods from the article by Sputin, we conclude that the logarithm is a locally nilpotent subset. Then we can prove our theorem. And these two facts are two lemmas, the bracket closure and local nilpotency. And then there is also some appendix, which I didn't know if I have time or not. So I haven't. On commutative nilpotent subgroups. There is a description by Regeta and Van Satten of maximal commutative nilpotent subgroups. And we have maybe simplified description in terms of exponents of some subspace of LNDs. We take just any set of LNDs S, which is a commutative set, and multiply it by the kernel in the field of function. And then the exponent of regular derivations in this subspace is exactly maximal commutative subgroup. It's a equivalent description. And we can prove independently that for commutative nilpotent subgroups, following conditions are equivalent. Well, it is maximal among commutative subgroups. It is generated by a generic frame, and there exists principal cylinder X sub H, such that U consists of all translations along fibers of the cylinder. These three conditions are equivalent. And next, there is also a description of some criterion when the given maximal commutative nilpotent subgroup R is contained in a generalized subgroup. Well, it uses the notion of a triangular generic frame, and I won't go into detail on it now. The results present here, and some idea of the proof. It's probably the proof is more complicated. It's just a first idea, but it works somehow. And finally, we have a criterion on maximality. If a generalized group is not maximal, well, if there are two commutative nilpotent subgroups, J at H, such that H is a subgroup of J and G. And it is the same width, so H is same width of J, but this bigger group G is not. No, maybe I cannot explain it right now, the criterion, but it is. And finally, there is some also some slides on other topics, which I won't show right now. Because, so they'll show that we have 5 main papers for this talk. And thank you again.
Sorry, but I didn't understand. These other topics, they are secret somehow. Why didn't you show them?
No. I just some also recent topics, electricity and automorphism groups. I just had some list of results that I could think of, and you can just. I think it is not complete, and but it was a pleasure for me to compose it. Because in some concise way. Yeah, that's all. Just tetrachrom of the groups, invariantness, simplicity, and electricity. That's why this. Thank you.
Thank you very much for your very detailed and full of result talk. Dear colleagues, please. Do we have any questions, comments? So let us discuss.
So my question is whether there exists a relation between for local unipotent derivations, say, between the notion, in your terms, between the notion of width and the rank. On this example that you gave.
I have no idea, because for local unipotent derivation, well, one local unipotent derivation, it generates a subgroup of width 1, because it has one-dimensional orbits, and its rank can be different. Maybe there is some relation that, for example, if we have a good question is to study generalized subgroups of width n minus 1n, where n is dimension of variety. For example, if we have an affine space of dimension n, and one of LNDs has positive rank, well, has some large rank, then we have some constraint on width of possible group which Lie algebra contains this derivation. So there should be some relation for unipotent subgroups. So if we have elements of large rank, then width is can be bounded. So probably yes.
Sorry, sorry, I didn't understand the question. So, Mikhail Grigorovich, your question is whether the width is equal to the rank. What do you mean by rank? The right length, or what is it? What is the rank?
I think it's the rank of another LND, right?
The rank of LND.
Like, yes, in terms of
okay, so the
number. Yeah.
I think there is a relation in dimension 3, but only in dimension 3. So in higher dimensions, we don't know it.
Okay.
I mean, in dimension 3, I mean for A3. But in general, it's probably even wrong. But
Andrei, what if we have n minus 1 derivations, and one of them is of rank 2? Then we have a maximal.
Okay. So
let me formulate it here. We have J of D1 star D n minus 1. In an to the power n, and we have D1 of rank 2.
Then
Maximal.
what I rather means that there is some kind of inequality. I don't remember it. So Michael Chetayat told me once that he has some inequality, but I don't remember which one. But there is no equality as far as I remember.
I guess so. I think that this case that I wrote down is contained in that inequality.
Mm-hmm.
Yeah, I think we just don't know all the possible pairs of width and ranks of derivations. We don't know all the possibilities, but we could probably remove some possibilities. Like if you assume width k, you can probably say something about the rank, and vice versa. If you assume some ranks, you can probably say something about the width, but we don't know all the possibilities yet. I guess that doesn't really help much.
That would be very interesting. Yes.
Okay. Thank you.
Okay.
So please, any more questions, comments? Let me ask a general question. Can you summarize somehow? So if we take classical theory of linear algebraic groups, then there is a beautiful part concerning unipotent groups. Say all maximal unipotent subgroups are conjugate. Say orbits of unipotent group action on affine varieties are closed, and so on and so forth. If we move to the case of unipotent group inside of the automorphism group of affine varieties, so this is the subject of your talk, certainly the situation is much more complicated. But can you list somehow which general facts do we have? So what is the structure theory at the moment?
I think that the general fact is this proposition that we can choose a cylinder such that our group is contained in the Jonquières group over the base of the cylinder. That's it.
It looks rather technical, so no more general facts. I don't know, just to underline them, not?
Well, certainly we also know that orbits are closed. I think.
Yes.
So, but it's not much. It's not much.
Yeah,
And
there's
the situation.
the cylindric structures with different groups that you cannot conjugate one to another. Even the dimension are different, like in examples.
Yes. Bits are different, and we can say the derived length is k is equal to it.
Okay. Dear colleagues, but we cannot finish with such a pessimistic observation. So let us ask something optimistic.
I'm sorry, can I ask? There was a talk about Borel subgroup, and your talk is about maximal unipotent subgroup. Is the connection between these kind of groups the same as in algebraic situation? So you just add a torus and obtain from unipotent subgroup a Borel subgroup, or you have something else?
If I understand right, the answer is yes, but the question is maybe I'll ask Michael to answer.
Yeah, so as it looks to us like if you have a Borel subgroup of an affine variety and you take the unipotent radical, then you get a maximal nested unipotent subgroup. And for every maximal nested unipotent subgroup, there exists a unique Borel such that its unipotent radical is that subgroup. So we think that's true. We still have to write it up and post it. But yes, we think we have a bijection between those two objects.
So I think Michael is right, but essentially I should say that this follows from Immanuel's talk. So this is Immanuel's talk that between, so that if you have a maximal nested unipotent group, so that solvable group is a union of solvable connected group is a union of its algebraic subgroups. So, and once it's union of its algebraic subgroups, from here, I think Immanuel stated it, that we have also that it's a semi-direct product of a torus and its unipotent radical. So basically, at least this statement, that a Borel subgroup is a semi-direct product of algebraic torus and its unipotent radical. I think, if I'm not mistaken, it was stated already in Immanuel's talk.
Okay,
Immanuel,
thank
can
you.
you correct me?
Okay.
So if
So Emmanuel is not longer here. Okay.
No, that was my question to Emmanuel during the talk. That was not clear from his talk. But finally it was okay, yes.
Dear colleagues, do we have any more questions, comments? If not, then let us thank Sasha for excellent talk. Thank you very much.
Thank you.
Thank you, Sasha.
And
Thank you.
Thank you.
our next seminar will be in April, and we expect a talk by Michel Brion.
Yeah, we do expect.
We do expect. So, okay. So, dear colleagues.
He promised the title shortly.
So we will obtain title and abstract and hope
Sure.
to.
No, title is already on the website. I'm sorry. Abstract will come shortly.
And it's the 6th of April?
I don't remember what is the first Monday in April. 6th.
Okay.
Yeah, 6th of April. Yeah, it's 6th.
Okay.
Okay, so perfect.
Thank you.
Thank you very much. See you in April.
Goodbye.
Goodbye.
Bye.
So, Adriana and
Bye.
Giancarlo.